Invasive aquatic species and intensive aquaculture operations represent two interconnected challenges facing coastal communities and marine ecosystems worldwide. The case of Australian redclaw crayfish establishing populations in Texas Gulf Coast waters, combined with the high-stakes economics of commercial lobster farming, illustrates the complex and often problematic relationships between human economic activities, biological systems, and environmental consequences that can spiral beyond initial intentions or control. Australian redclaw crayfish are native to tropical and subtropical regions of northern Australia and Papua New Guinea, where they inhabit freshwater rivers, streams, and billabongs. In their native range, these crustaceans occupy specific ecological niches where they're constrained by natural predators, including fish and waterbirds, competitors for food and habitat, parasites and diseases that have co-evolved with them, and environmental conditions that limit their distribution and abundance. These crayfish are medium-sized crustaceans, typically reaching 200 to 600 grams at maturity, with distinctive blue-green coloration and prominent claws that give them their common name. The biological characteristics that make redclaw crayfish attractive for aquaculture also make them formidable invasive species. When they escape cultivation facilities and establish populations in non-native environments, they demonstrate rapid growth rates, reaching market size in 6 to 12 months under favorable conditions compared to several years for many other crustacean species. They tolerate exceptionally wide ranges of temperature and water quality conditions, surviving in environments that would stress or kill more specialized species. They're omnivorous and highly opportunistic feeders, consuming whatever food sources are available, including plant matter, aquatic invertebrates, fish eggs, smaller crustaceans, and carrion. Their reproductive capacity is substantial and concerning from an invasion management perspective. Females can produce multiple broods annually under favorable conditions. With each clutch containing several hundred eggs. The eggs develop attached to the female's abdomen for several weeks before hatching as fully formed miniature crayfish rather than vulnerable free-swimming larvae. This reproductive strategy, where offspring are relatively well developed at birth, dramatically increases survival rates compared to species with extended vulnerable larval stages. A single female and her descendants could theoretically produce thousands of offspring within a single year under optimal conditions. When redclaw crayfish were introduced to aquaculture operations in Texas during the 1990s and early 2000s, the intentions were economically rational and seemingly beneficial. Aquaculture developers sought to create alternative income sources for coastal communities facing declining wild fisheries, diversify seafood production beyond traditional species, and tap into growing markets for specialty crustaceans. Texas coastal waters, with warm temperatures, abundant natural productivity, and established aquaculture infrastructure, appeared ideal for crayfish cultivation. Initial operations showed promise. Redclaw crayfish grew well in ponds, tolerated the environmental conditions, and produced marketable product. However, the containment systems used in many facilities proved inadequate for preventing escapes. Heavy rainfall events flooded ponds, allowing crayfish to escape into surrounding waterways. Hurricanes and tropical storms damaged infrastructure, releasing cultured populations. In some cases, failed aquaculture operations simply abandoned sites without properly disposing of stock, effectively releasing breeding populations into local waters. If you love our fishing documentaries, make sure to hit that like button, subscribe, and comment which country you are watching this video from to support our work and bring you more amazing videos. Once established in wild populations beyond cultivation facilities, redclaw crayfish created cascading problems for existing aquaculture operations, wild fisheries, and natural ecosystems. They competed directly with native crayfish species for food and habitat, often outcompeting them due to their larger size and aggressive behavior. They consumed the eggs and juveniles of commercially valuable species, including various shrimp species, blue crabs, and fish. Their omnivorous feeding destroyed aquatic vegetation that provided habitat for native species. Their burrowing behavior destabilized pond banks, levees, and natural stream banks, causing erosion and infrastructure damage. For existing aquaculture operations, particularly shrimp farms, the invasion created immediate and severe economic impacts. Redclaw crayfish found their way into shrimp ponds, where they competed with cultured shrimp for expensive supplemental feed, reducing growth rates and extending production cycles. They directly preyed on juvenile shrimp, causing mortality that reduced final harvest quantities. Their presence contaminated harvests, requiring additional sorting labor and potentially affecting product quality perceptions. They damaged netting, pond liners, and other infrastructure through their burrowing and foraging activities. Clam aquaculture operations experienced similar problems. Crayfish foraging in clam-growing beds disrupted the substrate, buried or exposed clams, and directly consumed smaller individuals. The physical disturbance reduced clam growth rates and survival, while the predation directly reduced harvestable populations. Oyster operations face challenges from crayfish climbing onto oyster bags and cages, potentially spreading fouling organisms and creating handling complications during harvest operations. The cumulative economic losses to Texas coastal aquaculture operations from redclaw crayfish invasion reached millions of dollars annually as the problem expanded and intensified. Individual farmers reported production losses ranging from 20 to 40% in affected facilities. Some operations became economically unviable and ceased production entirely. The costs extended beyond direct production losses to include increased labor for monitoring and removal efforts, infrastructure repairs, and the opportunity costs of reduced productivity. Control efforts faced substantial biological and logistical challenges that prevented effective eradication or even significant population reduction. Trapping represented the most practical control method, using baited traps to capture crayfish from ponds, canals, and natural waterways. Initial trapping efforts removed impressive numbers, thousands of crayfish from individual sites. However, given the species' reproductive rates and the difficulty of achieving complete removal, trapping struggled to keep pace with population growth and recolonization from the crayfish demonstrated behavioral adaptability that reduced trapping effectiveness over time. They learned to avoid traps or to steal bait without entering trap mechanisms. Their nocturnal activity patterns meant they were most active when trapping efforts were minimal. Their ability to survive extended periods out of water allowed them to migrate overland between water bodies, bypassing barriers and recolonizing areas that had been cleared. Chemical control methods using pesticides or biocides carried substantial risks of harming non-target species, damaging water quality, and affecting the aquaculture operations the control efforts were meant to protect. Regulatory restrictions on chemical use in aquatic environments, particularly near commercial aquaculture facilities, limited this approach. Biological control through introducing specialized predators or parasites risked creating new invasive species problems, as numerous historical examples demonstrated the dangers of introducing organisms for pest control purposes. Habitat modification to make environments less suitable for crayfish often conflicted directly with maintaining conditions favorable for desired aquaculture species. Most interventions that would discourage crayfish, such as reducing water temperatures, altering salinity, or removing vegetation, would equally affect or harm cultured shrimp, fish, or shellfish. The result was an ongoing management challenge without clear solutions, requiring continuous effort and expense simply to limit rather than eliminate the invasive population. This situation illustrates broader patterns observable across numerous aquatic invasive species cases globally. Many of the most problematic invasive aquatic species were originally introduced intentionally for aquaculture, either escaping from cultivation facilities or being deliberately released when operations failed or species proved unmarketable. The very characteristics that make species valuable for aquaculture, rapid growth, broad environmental tolerance, efficient feed conversion, disease resistance, and prolific reproduction are precisely the traits that make them successful invaders when they enter new environments lacking their natural population controls. The Australian redclaw crayfish case parallels situations involving Asian carp in North American waterways. Tilapia escapes in numerous tropical and subtropical regions, various shrimp species establishing outside their native ranges, and countless other examples where aquaculture introductions became ecological and economic problems. These cases collectively suggest that risk assessment for aquaculture species introductions requires much more careful evaluation of invasion potential and much more stringent containment protocols than were historically employed. Meanwhile, examining the economics and operations of commercial lobster aquaculture reveals different but equally complex challenges facing marine resource industries attempting to satisfy market demand while navigating biological, environmental, and economic constraints. Lobster aquaculture developed primarily in response to declining wild populations and steadily increasing market demand for these premium crustaceans that command extraordinary prices in global seafood markets. Wild lobster fisheries face mounting pressures from multiple directions. Overfishing reduced populations in many traditional fishing grounds, though management improvements have allowed some recovery in well-regulated fisheries. Habitat degradation from coastal development, pollution, and bottom disturbance affects lobster populations by eliminating shelter and nursery habitat. Climate change impacts lobster populations through warming waters that alter distributions, affect larval survival, and potentially increase disease susceptibility. The combination of these stressors makes wild catches increasingly unreliable and expensive. As wild lobster becomes scarcer and more costly, aquaculture appears to offer potential for stable, predictable production that could meet market demand while reducing pressure on wild populations. However, lobster aquaculture proves technically challenging and economically demanding in ways that distinguish it from more established aquaculture sectors like salmon, shrimp, or tilapia farming. Lobsters present unique biological challenges for aquaculture production. They're highly cannibalistic, attacking and consuming smaller or recently molted individuals when confined together. This behavior requires either individual separation of animals, extraordinarily space and labor-intensive, or maintaining very low stocking densities that reduce production efficiency. They grow slowly compared to fish or shrimp, taking 5 to 7 years to reach market size for cold water species like American lobster, though tropical species grow somewhat faster. This extended production cycle ties up capital for years before generating revenue. Lobsters are sensitive to water quality parameters, requiring excellent filtration, high dissolved oxygen levels, and careful control of ammonia, nitrite, and other metabolic waste products that accumulate in culture systems. They're susceptible to shell diseases and other pathogens that can devastate populations maintained at high densities. Their complex life cycle includes multiple larval stages with different environmental requirements, making hatchery production technically challenging. All these factors combine to make lobster aquaculture significantly more difficult and expensive than farming faster-growing, more tolerant species. The economic model for lobster farming requires substantial capital investment in infrastructure including tanks or cages, water quality control systems, feeding mechanisms, and monitoring equipment. The long time horizons before harvest generate revenue mean that investors must wait years to see returns. Throughout the extended grow-out period, careful management is essential to minimize mortality from disease, cannibalism, water quality problems, or equipment failures. These factors make lobster aquaculture considerably riskier and more expensive than farming species with shorter production cycles and more forgiving biology. Modern lobster aquaculture operations employ several different approaches, each with distinct advantages and challenges. Some facilities operate complete life cycle operations, raising lobsters from eggs collected from females through the multiple larval stages to settled juveniles and eventually to market-size adults. This approach requires the most sophisticated infrastructure and expertise, but provides complete control over genetics and animal health history. Other operations purchase juvenile lobsters from specialized hatcheries and focus exclusively on the grow-out phase, reducing technical complexity but depending on external suppliers for stock. The most intensive operations maintain lobsters in land-based recirculating aquaculture systems where all environmental parameters are controlled through filtration, heating or cooling, oxygenation, and sterilization. These systems offer maximum control and can be located anywhere with adequate water supply and infrastructure, but they have the highest capital and operating costs per unit of production. The energy requirements for maintaining water quality and temperature in large-scale recirculating systems are particularly substantial. Offshore cage culture represents an alternative approach that leverages natural ocean waters while maintaining population control. Large cages or pens constructed from durable materials are anchored in suitable locations with good water exchange from natural currents. These systems utilize the ocean's natural capacity for waste assimilation and oxygen renewal, dramatically reducing operating costs compared to land-based systems. However, offshore operations face significant challenges from weather exposure, potential predation by seals or large fish, biofouling of cage structures by marine organisms, and the substantial logistical difficulties of servicing cages located in open water potentially far from shore. Weather conditions present particularly acute challenges for offshore aquaculture operations of any type. Major storm systems with high winds and large waves can damage or completely destroy cage infrastructure, potentially releasing the entire cultured population and causing total production losses. The anchoring systems must be engineered to withstand extreme forces while maintaining cage positions. The cage structures themselves must be robust enough to survive violent wave action without failing. Even if physical damage is avoided, storms can stress cultured animals through rapid environmental changes, potentially triggering mortality or making them vulnerable to disease. The timing of harvests relative to weather patterns and seasonal storm risks becomes a critical management decision. Operators must constantly balance the economic value of allowing animals additional time to grow against the probability and potential consequences of storm damage before harvest can be completed. Forecasting provides some predictability, but forecast accuracy decreases for longer time horizons. Decisions about whether to harvest immediately or wait for additional growth involve complex probability calculations weighing expected value of additional growth against risk-adjusted potential losses from weather damage. When the decision is made to conduct a major harvest operation from an offshore lobster farm, the logistics are substantial and time-sensitive. Vessels must be chartered and crews assembled. Equipment for safely retrieving cages or their contents must be prepared and deployed. Weather windows must be identified when sea conditions allow safe operations. The entire process must be coordinated to move efficiently through the sequence of retrieving animals, sorting and grading them, providing appropriate temporary housing with life support, and transporting them to shore facilities. The harvest operation itself combines elements of marine construction work, fishing operations, and livestock handling. Cages containing market-sized lobsters must be lifted to the surface using vessel-mounted cranes or brought alongside boats for access. Workers must enter the cages or use specialized equipment to remove lobsters without injury to either the animals or handlers. Lobsters can inflict painful injuries with their claws. Retrieved lobsters must be sorted by size and quality, then placed in containers with adequate water circulation and oxygen to maintain health during transport. The speed and efficiency of harvest operations directly affect product quality and economic returns. Lobsters experience stress from handling, changes in water conditions, and crowding during transport. Extended time in suboptimal conditions can cause mortality. reduce meat quality, or make animals lethargic and less marketable. The goal is moving animals from ocean cages to shore-based facilities as rapidly as possible while maintaining conditions that preserve their health and vigor. Shore-based processing facilities must be prepared to receive and handle large volumes of live lobsters arriving from harvest operations. Holding systems with high-capacity filtration and oxygen supplementation maintain lobsters in good condition until they're sold or processed. Live lobsters command the highest market prices, but require the most sophisticated handling, storage, and distribution infrastructure. Processing alternatives include cooking and freezing whole lobsters. Extracting meat for various products, or producing value-added items like lobster bisque or prepared meals. The premium seafood market drives demand that makes lobster aquaculture economically viable despite its challenges and costs. High-end restaurants purchase live lobsters for preparation as luxury menu items that can command prices exceeding $50 to $100 per plate. Retail markets sell both live lobsters and various processed products to affluent consumers willing to pay premium prices for quality. International trade moves lobsters from production areas to consumption centers worldwide, with Asian markets, particularly China, Japan, and South Korea, representing increasingly important destinations that pay exceptional prices for live premium specimens. The economics of a successful harvest from a well-managed offshore lobster farm can be substantial. An operation producing 10 tons of market-sized lobsters, roughly 10,000 individual animals at average size, might generate $400,000 to $500,000 in revenue, depending on market prices, product form, and distribution channels. This revenue represents the culmination of multiple years of investment, ongoing operating costs throughout the grow-out period, and successful navigation of the numerous biological, environmental, and logistical risks inherent in growing valuable animals in unpredictable marine environments. However, this potential return must be weighed against the substantial costs and risks involved. Initial capital investment in cage systems, boats, monitoring equipment, and shore facilities can reach millions of dollars. Operating costs including labor, feed, maintenance, insurance, and monitoring systems continue throughout the production cycle. The risk of partial or total loss from storms, disease outbreaks, equipment failures, or market price fluctuations means that individual production cycles might generate losses rather than profits. Only operations that successfully manage these challenges across multiple production cycles achieve sustained profitability. The operational reality of lobster aquaculture combines biological understanding, engineering capability, logistics management, market knowledge, and constant risk assessment. Monitoring systems track water quality parameters continuously, alerting operators to potential problems before they become critical. Feeding protocols must account for growth stages, seasonal environmental variations, and nutritional requirements that change as animals mature. Health management requires vigilance for early signs of disease or stress, and rapid response capabilities to address problems before they spread through populations. The contrast between uncontrolled invasive species proliferation and intensive aquaculture management highlights fundamentally different aspects of human relationships with aquatic biological resources. Invasive species like Australian redclaw crayfish represent cases where biological success, traits that allow organisms to thrive and reproduce prolifically, creates economic and ecological problems. These organisms excel in new environments precisely because they lack natural population controls, and their success comes at the expense of existing ecological communities and human economic interests. Aquaculture represents the opposite dynamic, humans attempting to control and optimize biological production through intensive management. Yet this control remains imperfect and challenging, as demonstrated by the technical difficulties, economic risks, and environmental concerns associated with lobster farming. The attempt to cultivate marine organisms for economic benefit requires constant intervention to maintain conditions that differ from natural states, and outcomes remain uncertain despite sophisticated management. Both situations involve species moved by humans into new environments or new contexts, whether through deliberate introduction for aquaculture that subsequently escapes, or through intentional cultivation in controlled settings. Both create significant economic impacts on coastal communities, though the directions differ. Invasive species impose costs, while aquaculture aims to generate revenue. Both require ongoing, intensive management efforts, either to control problems or maintain productivity, and both illustrate fundamental challenges in predicting and controlling outcomes when biological systems interact with economic pressures, human technologies, and variable environmental conditions. The Australian crayfish establishing in Texas coastal waters and the lobsters being cultivated in offshore cages represent different expressions of the same underlying dynamic. Humans attempting to harness marine biological resources for economic benefit, while dealing with the unintended consequences, inherent uncertainties, and management challenges that emerge from working with living systems in complex, changing environments. Neither situation offers simple solutions or guaranteed outcomes, but both reveal the intricate and often problematic connections between biology, economics, technology, and environmental management in contemporary marine